Let's go ahead and start up again. We're going to have Steve Fenter from U.S. Bank talk about the data center problem and what things are inside. I'll give you one brief story of, I think it was one of our very first conversations. You see Steve, he's one of the calmest people I've ever met. And I was, you know, people for a long time, I've been telling people, you guys really need to go to the ITEF and so on. And a lot of companies are like, yeah, you go and tell us what happened. And then, so I'm like, okay. So then I was telling these guys, you know, this happened. And then when I told them about deprecating RSA, he went ballistic. He's like, what are they doing? Where is it? Where does it say that? And so I pointed it out, had him read everything. And it was funny because it was like, that was on Thursday. Lots of email exchanges, phone calls over the weekend. By Monday morning, they're like, he's going to Berlin with you. So here's Steve.
Okay, I'm going to try to talk about why we care about TLS 1.3 and why we care about losing the RSA key exchange. I'll apologize ahead of time to a couple of you who've heard this presentation or something close to it. Hopefully it'll sink in really good the second time. It's new material for most of you in the room, I think. So with that, I will move forward. There we go. So you've heard some of this already. The big problem is losing the RSA key exchange, which takes away our ability to take an RSA private key and put it into Wireshark, or put an RSA private key into an SSL decryption appliance, or put an RSA private key into an application performance monitoring box, et cetera, et cetera. We have no more capability, or if nothing is done, we'll have no more capability to do out-of-band TLS decryption where we put a passive tap in, send the packets to a tool, and decrypt them. Are we okay?
You know, people are saying they can't hear that well. Just try that.
Yep. So a couple of words about, can you hear okay now? Is this better? A couple of words about the impact, and some of this is going to be our own experience at our own company, but just to give you some ideas. Fraud monitoring systems are big in the banking world, and they're an absolute requirement for you to log in to things like internet banking. It depends on decrypted packets that are done out of band today. And if fraud monitoring is down, it's a severity 1 outage to our most critical applications. And it's required by regulatory requirements as well, so it's not an option. And the loss of out-of-band decryption at the moment is going to kill fraud detection. IDS, IPS, you know, there are things you can see with an IDS when the packet is decrypted, like an SQL injection attack, which I've seen on sniffers. It's as plain as day. There's a big select statement if you're looking at a sniffer of a decrypted packet, but it's not so obvious to the IDS if you are looking at encrypted packets. Also, another point about IDS is it's not just something to do for things coming in the door of the internet. For example, if you're a PCI company like banks are, you're required to do IDS monitoring of the cardholder data environment. And the cardholder data environment is not just one place, at least in most enterprises. There are many cardholder data environments that need many IDSs that need decryption if you're going to find stuff on the IDS. So the problem with inline decryption, which is one of the solutions given to us by the IETF, is that it doesn't scale. And IDSs, well, I can't give away too much internal detail, but we have lots of monitoring points for IDSs and other security tools, and it's too many to try to replace with inline solutions. And inline solutions have 3 problems. They're expensive. They add production risk. If my monitoring solution fails, I'm bringing my production traffic down. And they add latency. And the more inline solutions you string together, the more cumulative latency you're adding. So inline decryption is great, but it doesn't scale for the needs of an enterprise. Malware detection, tools like FireEye and security analytics can find a lot more stuff with decrypted packets than they can find with encrypted packets. Layer 7 DDoS protection. This is something primarily on the internet, but just as an illustration of why decryption is important. We had a lot of DDoS attacks back in 2012, 2013, as did most financial institutions in the United States. So we had a lot of experience with it. The guys that did it, fortunately, were very polite about it. They said, we're going to DDoS you at 8:30 on Tuesday morning. And they were true to their word. At 8:30 Tuesday morning, a DDoS attack came, which was great. We didn't have to be up all night. So I thank them for their courtesy, but we got a ton of DDoS attacks. All the banks did. So one of them in particular that I looked at was a layer 7 attack, which was not volumetric enough to be blocked by our internet-based, volumetric DDoS protection. It was getting through to our stuff. And fortunately, we had taps on our internet routers, and we had sniffers off of those, and we had the capability to decrypt inbound attacks. And we could see this thing was requesting a large PDF file over and over, and it was killing our servers. And also, everything about this attack was changing. The source IP was changing, the source port was changing, so you couldn't block on an IP to stop this thing. And down in the payload of the packet, in the HTTP headers, all those headers were changing every time, except for one field that we found just kind of by luck that was staying the same. So our F5 guys were able to go into their F5 and put an I rule in there to block on this particular field, and that was successful in blocking the stack. And I think US Bank did pretty well during those attacks. We weren't totally down, really, ever. And we had some impact, but we weren't hugely impacted. So I think we did pretty well. And this is one of the reasons we of course, had some smart people looking at things, but we also had full visibility. And with no time lost, it was the packets came in, they were getting decrypted, they were going to the sniffer, and we could just start analyzing the problems immediately, which is crucial. Security incident response, these are the threat detection guys. Now, I don't do this for a job, so I'm speaking secondhand, but again, things like SQL injection attacks are obvious if you've got decrypted packets. But the other thing is, if you have an SQL injection attack, you're not just done in that you got an alert. You have to figure out whether the attack was successful and whether they got any data. So the threat detection guys are going into sniffers all the time, just like me, daily. They're looking at decrypted sniffer traces, trying to figure out if this attack was successful and if any data was returned. Or, another example they gave me is they detect a malicious PDF file on some server or workstation. Well, they need to know where that came from. So they're going into decrypted sniffer traces, trying to backtrack who wrote that file to that particular machine. So decrypted packet analysis is crucial for what they do every day. Regulatory verification. So being a bank, we have all kinds of regulations. And in fact, I just got a great email from one of our partners at the Financial Services Roundtable with this whole long list of all the different government regulations and what we're required to keep track of. So traders and all the trades that they've done and all their communication with partners, we have to save it for 5 years. And so it's just a long list. And I can say anecdotally that a number of there are financial institutions in a large way doing some of this monitoring with decrypted packets, using out-of-band RSA keys to decrypt, some of these communications and then store them and save them. And, one of their comments was, you don't want to do all this on the endpoint because the guy you're trying to monitor owns the endpoint and you don't maybe necessarily trust, his control of that endpoint. So you get a viewpoint on the network. And the same is true of malware. If an end station gets infected, the malware turns off your endpoint monitoring and deletes the logs. So you don't want to just completely trust an endpoint. So you get a viewpoint on the network. And so financial institutions are fulfilling regulatory requirements with out-of-band decryption, and it's a huge hit on them if they lose that capability. Wireshark PCAP decryption, that's what I do for a living. I'm a sniffer guy. And I will talk more about what it's like trying to look at traces that are encrypted versus looking at traces that are decrypted. And then another Impact is going to be network performance monitoring, application performance monitoring. So tools like CompuWare, you can tap the web tier and the app tier and middleware and database tier, feed that all into a tool like CompuWare. NetScout NG1 is another example. I think Diaby has a similar solution. So there's a number of network performance, application performance monitoring type tools. And if you can decrypt the traffic, you can create stats and dashboards by URL, not just by layers. So you can say, hey, the transaction history request to the back end is having problems, and you know exactly where to look. And without decryption, you have no idea which part of your infrastructure is impacted. Okay. So this is an example of one of our internet-facing applications. I've purposely made it generic to not give away too much internal information, but this is also a pretty common application infrastructure. And I purposely made it an eye chart to make a point. So just briefly what I'm showing here is at the upper left is where the internet users come in through the internet routers. And by the way, I've included all the routers and switches. I've included all the infrastructure like firewalls and load balancers and proxies, because when I get an incident call, the problem could be in any one of these 400 boxes. And my job as a troubleshooter, the first job is to isolate which one of these 400 boxes is my problem. So that's why I have everything. This is the entire infrastructure for this application. So you come in the upper left, you come through the firewall into the DMZ, you hit the load balancer, you hit a reverse proxy, and then you hit the middle two columns, which are the main processing paths. So there are web servers in there, there are app servers in there in the middle column, and again, a bunch of routers and switches. There are several layers of middleware getting near the bottom in the middle. There's a mainframe at the bottom. The lower left of the diagram is a bunch of authentication type infrastructure, LDAP, and that kind of stuff. The lower right is fraud monitoring. And then if the app servers are making service calls out the internet, that goes through the upper right through the internet proxies, and then load balancers, firewalls, and out the internet to companies like Fiserv that banks tend to call. So this is one application, and if somebody logs into this particular application and they have a slow response time or it fails, the problem could literally be in any one of these 400 boxes. And I often get incidents with application guys on the phone, and they may have no log entry at all anywhere. That happens sometimes. So they have a slowdown or a failure, no log entries anywhere, and they're saying, where is my problem at? Oftentimes, the firewall guys are on the phone. They may not have any log messages. The load balancer guys, or maybe there's a log message that says, this person's login failed, but no details about why it failed, or maybe it timed out. But if you get a log message that says this login timed out, it could still be anywhere in these 400 boxes as to where the timeout is, which this is the kind of stuff I deal with every day. Severity 1 problems, chronic problems that nobody else can figure out, not because they're stupid, but because they don't have visibility to see what's going on. And the sniffer guys oftentimes are wizards just because we have so much better visibility than other groups do, just looking at their logs. And if we can decrypt packets, I often say that if my team couldn't decrypt packets, it would eliminate 90% of what we're able to do. Literally 10% of the time, it's a basic network problem like packet drops and retransmissions. The rest of the time, we're chasing around application level problems and helping the app guys figure out where their problem is. Or maybe it really isn't infrastructure. Maybe it's a firewall problem. But the firewall guys have no log entries. Their CPU looks fine. They don't know that they have a problem until we put a sniffer above and below the firewall, and we see, hey, this packet took 200 milliseconds to get through the firewall. So I put a little note on here that we also have 2,000, we have to have more than 2,000 total unique applications at the bank. So take the complexity of this. Now, some of this is shared infrastructure, but the complexity multiplies exponentially because the next day we'll get a problem for a completely different application, a completely different set of boxes, and we got to go figure out where the problem is. So I tried an experiment to get to get a trace. This is a NetScout sniffer for, I know some of those folks I represent here. I took my mobile phone and I logged on to this particular internet-facing app just to demonstrate what it's like trying to look at a trace. And if you have a problem where a user out on the internet, for example, can't get to internet banking or they're getting slow response time, your first job as a troubleshooter is to isolate, is my problem out on the internet somewhere, or is it down in my database, or down in my data center somewhere? So the way you do that, or the best way, I think, is you take your tap right on your internet routers, right, where it hits Verizon, and you pull those packets into a sniffer, you analyze them, and you see if your delay or your failure is this way or that way. And now you know I go after the carrier, or I go after the content delivery network, or I go to my app guys or my infrastructure guys to keep working on the problem. So I traced myself doing a simple login, and what I did here was this is a trace on our internet connection, and I pulled out a minute before and a minute after my login attempt just to make sure I caught it all and didn't miss anything. And what I come up with is 3.6 million packets. So if any of you have looked at sniffers before, it's not easy looking at 3.6 million packets and trying to find anything that's meaningful. So the next page is an example. I hope, again, it's a little bit of an eye chart, but I changed the IP addresses to make them generic, but it doesn't matter because the IP address, if you have a content delivery network, is NATed, and what you see is the content delivery network IP address. You don't see the end user PC. So if I know what my IP address is, there's no way to find it in a sniffer trace because it's all NATed and we only see the content delivery IP address. So I'm stuck trying to even find my session out of 3.6 million packets. And if you look at, at the summary, there's a bunch of TLS packets, and there's some encrypted application. I'm highlighting some application data, which is encrypted down below. And there's literally nothing in here that will help me find my session. This is a needle in a haystack, except that there's no needle. It's actually hopeless for me to try to find my session in this encrypted trace. So we're blown out of the water before we even get started troubleshooting this problem. But if I can decrypt these packets, that's what the next slide shows, all of a sudden these light bulbs come on, and now I can see the true client IP, which was my mobile phone IP address for the test I did. It was a transient IP address, so it's not like I'm giving away a big secret. And the exported 4 has the same information. So now I can pull a trace into Wireshark. I can do edit find packet and look for my IP address, and I can find the different TCP connections that make up my my login. And just as kind of a side note, this is not exactly related. Well, no, it is related. When I did this experiment, well, actually, let me back up. In older days before content delivery networks, I could get an IP address of a user, go into the internet sniffer, mine out the packets, and within 2 minutes, I've got 3,000 packets and I'm looking at my problem. In the world of content delivery networks, I actually came from not only the wrong NATed IP address, but 5 different IP addresses. And I found some of them with true client IP. I found other ones by searching on my user ID. And between digging around with true client IP and user ID, I found these 5 sessions that I had to piece together. It took me 2 hours to just find all this stuff from my session. This is just an illustration of the complexity of today's environment when you're trying to troubleshoot a problem. There's natting and there's encryption. Everything is obfuscated. And my one session becomes 5 IP addresses. Everything is obfuscated, making life harder and harder and harder for the troubleshooters like me and also for the network security analysts. So eventually I did find my session. I did piece it all together and I was able to find my login. Here's another example of what it's like. A typical day in my life or the life of people on my team. You get the problems that nobody else can solve, the chronic problems, all the other teams are stuck. I think my record is being on a bridge call with 60 people on the call. And I've literally had all 60 people sitting in dead silence while they're waiting for me to mine out packets, decrypt them, look at them, and and give them an answer. Like 45 minutes of just dead silence, like we don't know where this problem is, please give us some kind of an answer. So this is a problem I actually worked on. It's been a few years ago now, but this is a real problem where a certain percentage of users out on the internet would log on to internet banking, and they'd get their login screen, and there's the piano keys are a kind of a security thing. You can choose an image, and if the wrong image doesn't come up, then you know somebody's hacked into your session. Or you can have a sound play. But there's supposed to be a password prompt down below that box, and it's not there. So they have no way to enter their password until they can't log in. They're stuck. So I got called on this problem from the application support manager, and he said, I'm sorry to keep bugging you, but I can't see anything. And he gave me a sample of the log. They did have log entries, and this is a pretty close approximation of the log entries they had. And I said, is this all you've got to go on? And he said, yes, this is everything. This is everything I have to go on. So basically, this is in 2-row segments. So, you know, the first entry says the guy entered his user ID in. And then to the right, he gets a challenge question. So he, if you remember my 400 boxes down in the lower right, there's more authentication stuff, and you get a challenge question like, what's your mother's maiden name? And then the second row, the box kind of in the middle there, that he puts in his challenge answer. My mother's maiden name is Rathke. That's my case. And then there's a box that says the answer was okay. And that's it. That's all there is. So based on this log, based on the symptoms that there's no password prompt in this log file, where is the problem? What is the root cause? And how do you fix it? That's what I have to deal with. That's what the app guys are trying to deal with. Where's the problem? What's the root cause? And how do you fix it? And I could wait for some responses, but I won't take the time. But I've tried this on people, and nobody's ever come even remotely close to what the root problem is just from the application log file. So the app guy said, you know, I think the problem's on the back end. So without anything else to go on, I started tracing the back end from the app server down to the authentication piece on the lower right in this case. And I was able to find these 4 pieces. I found it with decrypted packets. Okay, this is out of band decryption. I was able to find the user ID going back. I was able to find the challenge question, what's your mother's maiden name? I was able to see the answer, go back to the authentication piece, and I was able to see, hey, this is okay, come all the way back to the app server. So that told me, okay, I think the whole back end is there. I think that's fine. That's not the problem. So I've chopped off 1/3 of the fault domain. So then I decided I'll go into the internet router tab and look at the packets that are actually sent out. So this is what was actually sent out. This is the real screen. I matched it up in my sniffer trace. This is the login screen to this exact person going out. Decrypted. So based on this encrypted screen, where's the problem? What is the root cause? And how do you fix it? Right? So hopefully it doesn't take too long to realize, well, you know something went out, but you don't know if it was the whole screen, if it was part of the screen, you don't really know, right? But once I had a decrypted view of this thing, then again, all kinds of light bulbs come on. You can see in the gray here that I've highlighted, the word password is in the screen, which means that is the password prompt, and the box is defined there. So now I know the whole screen actually went out on the network. And I could see from the TCP layer that the screen was act. So I now know that the whole correct screen made it all the way out to the PC acted. So now I know I've ruled out all this fault. I mean, I know the problem is inside the PC somewhere. So we could say, all right, it's a Microsoft problem, close the ticket, go talk to Microsoft. But I actually looked a step deeper at the sniffer hex data. And what I found in the hex data, if you see what's written there on the upper right, if this is not your personal ID, or your shield image. See if I can get there here. If I go back to the screen, that's the verbiage here. That's the verbiage down here, the last thing that came out before it was chopped off. So we can see that being sent out. And then right at the point of the last thing at the bottom here, it says restart your login. That's the very last thing. And then there's this long string of zeros. And it took me a while for it to really sink in, but you know, that's not supposed to be there. It was a software bug. And I went back to the app guys and said, you know, this looks strange to me. Right at the point where this failed was this huge string of zeros. And it was somehow messing up the PC, either the virus scan or the browser or somebody on the PC was getting messed up with these zeros, and they quit outputting the screen. So I took this back to now this had been going on for 2 months. Major critical application, 2 months, it was intermittent. It wasn't full-on step one. It was intermittent, affecting a certain subset of users, but it went on for 2 months, and the app guys had no idea where the problem was. But I took this data from the payload of the packet, went back to the app guys, and the next day they had a fix. They quickly went in to their code, they found where it was happening, they found the bug, they fixed it. So again, this is application layer data in the application payload that solved this problem. So, you know, there are people in the IETF and other places that say, well, you know, you can just look at IP and TCP headers and figure stuff out. But for this problem, IP and TCP headers do nothing for you. People at the IETF say you can just look at logs. You know, well, you guys saw the log. What was in that log was in no way anywhere close to the root cause of this problem. We had to get the packets and we had to get to the payload, the application layer payload, to get to the root cause of this problem. Here's one more troubleshooting example, just to give you another illustration of what it's like. So this is the same diagram, but I've kind of zeroed in on the bottom middle portion of that first diagram. So there's middleware here, several layers of it. There's a bunch of infrastructure stuff in here, load balancers, firewalls, and then there's a mainframe at the bottom. And we had a problem where the middleware server at the top was making a certain call to the mainframe, and it was timing out. And the mainframe support guy said, hey, I got your request, and I immediately sent the response back. So now we're stuck. What happened to this? This is kind of like Nalini's illustration. What happened to this response? Well, it just so happens, well, first of all, there's like 75 or 80 boxes in here, any one of which could have been the cause of the problem. So how between all this stuff do you know where your packet went to? The other problem is with this particular mainframe protocol, you make a request. If you guys are, I'm trying not to give away all of our internal workings, but if you know IBM at all, you make a request and then that request gets farmed out to one of many mainframes and you don't know which one. That's why there's a bunch of them on the bottom. And the answer comes back asynchronously. So you don't know who's going to answer and you don't know when they're going to answer. So how do I find this packet without knowing? And it just so happens that the key to matching up the request and the response is down in the payload of the packet. You have to go down in the payload to find a certain identifier, and then you find that same identifier in the response, and you can say, okay, here's the request, here's the response that goes with it. And just to make it fun, I don't know if this is unique to us or not, but the request identifier is in ASCII and the response identifier is in EBCDIC, if there's any mainframe people here. And if you're just looking at ASCII, you've got no idea where in the world your response is. So but if you can't see the payload, you're completely up the creek. You have no idea if the answer came or not. So it turned out I was able to find the answer. I was able to follow it at least part way through this infrastructure to see how far it made it. And I found out that one of the packets of the response just disappeared and had to be retransmitted multiple times, and eventually it timed out on retransmits and it failed. So you might say, well, that should have been easy, right? Just go look for packet drops in this environment. But we had tried these are all core Nexus routers, switches. And you go look at these 40 gig or 80 gig port channels, and this one has 1 billion packet drops, and this one has 2 billion packet drops, and this one has 3 million. They all have packet drops because of, I don't know, backups at night, and it, you know, temporarily overwhelms. There's packet drops all over a normal core infrastructure. So how do you know which one is the right one? And the way you find out is visibility to the packets so that you can find your exact response, track it through the infrastructure, and eventually that will narrow you into the right place. So we eventually found this problem, but it took a while, and it took packet analysis to point to the right location. Okay, a little bit about security. Again, I'm not a security guy, so I'm not completely authoritative, but I do work with the security guys, with the threat detection guys. I help them find things on sniffers occasionally, and we also own the packet broker network, and we provide all the packet feeds to things like IDSs and security analytics. We provide decryption services so they can look at decryption packets. And this is just a little view of where all the security monitoring tools are. There's a bunch of them, and this is kind of meant to be a generalized view of the data center. It's not perfect, but it's meant to be more general. So, you know, in tier 1 and tier 2, there's a bunch of IDS and malware. Going out the extranet on the far left, there's again IDSs and malware detection. Down in the middle, and see, it's not just the internet. That's the point I'm trying to make here. We've got mainframe, fraud detection, internal fraud detection going on. We've got IDSs on PCI enclaves. The threat guys are interested in DNS servers. They're interested in wireless controllers. In total, it's 150 physical tap points feeding network security monitoring tools. And it's too many to replace all of these with inline solutions, which is what the ITEF guys tried to tell us originally. It's millions and millions and millions and millions of dollars, plus production risk, plus latency to try to put inline solutions in all these places to get the packets we need. So again, the key is we've got to have an out-of-band decryption capability. A passive tap is like, passive taps just never fail. We've been doing this quite a while. An inline decryption solution can fail. Passive taps never fail. They're like a gold mine of information with no risk. It's the absolute perfect solution for an enterprise. And to take away that capability and say, you got to put all these inline solutions at a cost of $50 million and you're going to risk all these outages, that's not attractive from an enterprise perspective. A passive tap that never fails, and this gold mine of packet data for all these different purposes, for fraud, for troubleshooting, for application performance monitoring. It's too much for inline solutions. Here's a few words about threat detection and incident response. Again, I'm not a security guy, but this is kind of what I've gleaned from our threat detection team. So they find a lot of SQL injection attacks, as I mentioned before, but you have to know if it was successful or not, and that's packet analysis of decrypted packets to figure out if the attack works or not. IDSs get a lot of false positives. So the threat detection guys are pulling up sniffer traces, looking at decrypted packets to figure out if this particular IDS alert was real or if it was a false positive. They do a lot of manual hunting. So just like me, who manually looks at sniffer traces to figure out what's going on, they're manually pulling out decrypted packets, looking for, maybe they've gotten an alert or, you know, a email about a particular threat that's out there, and they start digging around decrypted packets to try to find them. And antivirus alerts, that's what I alluded to before. Maybe you've got a malicious PDF file and you want to know where it came from. So again, that's decrypted packet analysis to figure out where did that PDF come from that infected the workstation. And then the last note I threw in, because there are forces in a number of places that are trying to say, well, you can just look at encrypted packets and that's good enough. And there are people that have done fancy heuristics on encrypted packets. Cisco is one of them that's pushing this in a fairly big way. And they're doing some good work. They're finding things through encrypted patterns where they can say, hey, this is this kind of malware, or this looks like this kind of attack. So what they're doing is fine, but the point I'm trying to make is the things that they're doing are not going to solve every problem. Now, one simple answer, they're looking for malware. They're not going to solve my severity 1 problems. So the one I showed with no password box, you know, they're not doing anything to solve that problem. And they're not going to find every malware attack. They'll find a certain percentage, which is great. But I've heard this. I was at the RSA conference last year. There was a session on, you know, looking at encrypted packets, and we can find this and that. I think it's, well, I'll try to say this the right way. There's nothing wrong with what they're doing, but it's a ton of work, and it only gets you so far. As long as people don't make it, the end all that this is going to solve every problem, because it's not. We need decrypted packets to solve the rest of the problems that heuristics on encrypted packets won't solve. So just so I'm clear about the use cases we're talking about, one of them is after the fact. Maybe I had an outage over the weekend and I get a ticket on Monday. I can go in, if we have a large sniffer like an InfiniStream or a Gigastore, I can mine out packets. I can put them into Wireshark. I can put a private key into Wireshark and decrypt those packets. Or if you're farther along, you have an HSM and you have your keys in an HSM and you use a sniffer tool that's able to talk to an HSM and get that key. But out of band after the fact with something like Wireshark is one use case. Another use case is live decryption. So, Symantec makes an SSL decryption appliance. Some of the packet broker vendors are doing the same thing. You can decrypt on the fly. Some of the tools, some of the fraud monitoring tools, you put a key into them and they decrypt on the fly. Or application performance monitoring, again, you can put a key in, decrypt on the fly. So these are the two main use cases we're trying to solve. After the fact, Wireshark type decryption, and on the fly, live, where you got to keep up as the packets come by and get them decrypted. So to try to summarize a little bit, Darrin and Nalini and I have been talking to a lot of people in the last year and a half about this problem. And we found partners, people that do the job that I do, troubleshooting, people that do security. We know that many other large financial institutions have the same problem we do, and they need an out-of-band decryption capability. We know people in healthcare that need to decrypt. We've got contacts in retail that are decrypting packets, that need to decrypt packets. Government has the same problem. So it's not just a financial problem, it's an enterprise-wide problem. For any enterprise that sees the need to encrypt their data inside their enterprise, and this is kind of a gradual, progression. I think banks and healthcare are early on adopters of encryption inside the enterprise because of PCI and because of HIPAA. Those are big drivers, and just because we're protecting people's money. But I think other industries are also moving this direction. And I think we're raising our hand first because we were early adopters of encryption inside the data center. But I think there's going to be a growing awareness among other industries as people say, hey, we better encrypt stuff inside. They're going to find out that they're going blind, and they're going to need decrypted packet access as well. So it's not just financial, it's any enterprise that's encrypting. And again, it's kind of a gradually growing movement. And I think both Darrin and Nalini have alluded to the RSA key worked great, but for a number of reasons, we're not going to get it back, not the least of which is TLS 1.3 is really different from TLS 1.2, and the handshake has been completely hacked up and completely redone, and the client key exchange is completely gone, and it's just really far down the road. Plus, the guys that know cryptography well, again, as Nalini alluded to, is RSA has more weakness as the computing power increases, and Diffie-Hellman is more cryptographically sound. So RSA is not coming back. The last point comes from another comment from ITEF people. Can't you just run TLS 1.2 in your data center? Run TLS 1.3 on the internet, terminate it in a load balancer, run TLS 1.2 inside. And yes, that does work for the short term, but eventually we're anticipating that TLS 1.2 isn't going to last forever. Just like TLS 1.0 and TLS 1.1 have had vulnerabilities found, and you fix that by upgrading to TLS 1.2. We're anticipating that vulnerabilities will be found sometime in TLS 1.2. And then you've got regulators like PCI that say, hey, you've got to upgrade your TLS if you're going to be PCI compliant. So I don't know how soon it's going to happen, but I think we're going to get stuck if TLS 1.2 is our only solution, right? You can't, it would be like saying just run TLS 1.0 forever, right? That's not a viable solution, and TLS 1.2 probably isn't going to be viable forever either. So we need a solution in TLS 1.3 that works to give us an out-of-band decryption capability. I think I just said this, right? You could run TLS 1.3 on the internet, you could terminate TLS in your load balancer or your internet proxy, and you can run something else inside your data center. it's TLS1, can be TLS 1.2 today, but in the future we need some kind of solution with TLS 1.3 out-of-band decryption. So this kind of meets everybody's needs, right? The people concerned about oppressive governments on the internet, you can have real ephemeral Diffie-Hellman TLS 1.3 on the internet, but for people like me that are inspecting things inside the data center, I can run an out-of-band solution. So what are we up to? This is a similar presentation to what I did for the TLS working group. Jason Whitty, our CISO, and I went out to Korea in November and presented something very much like this, a much more condensed, shorter version, but, and this is one of our slides for the TLS working group, that we want to collaborate with them. We want an enterprise-centric solution that's well-studied and interoperable. And as you think about it, right, we've got a bunch of TLS vendors. We've got load balancers, we've got browsers, we've got data center servers, Microsoft, Linux, we've got mainframes. And we would really like all of them to fix this problem in the same way, right? So that's why we want a standard, so that they all do the same thing, so that our tool vendors can just do one thing and it works with every TLS server or client in the world. So we want a standard. I've listed here a draft. This is actually our second iteration. I won't go into too much detail because I think Nalini is going to do this part, right? Like what's been happening in the IETF. But just really briefly, we submitted a proposal in July that uses a static key for Diffie-Hellman, just like an RSA static key. And through various machinations at that Prague meeting, we ended up with, we sort of support the idea that we need to do this, but static isn't the way we want to go. So we're coming out with a new draft. Actually, today is when it's supposed to be published and an email posted on the TLS email list. So I'll leave it to Nalini, or maybe both of us will go into a little more detail on what the solution is that we're proposing. We need a standard so that everybody does it the same way. This is just another little teaser, because one of the things we're after is to get more people involved at the IETF. And I think there's a lot of enterprise people like me that were completely clueless about what's happening. And, you know, I'll just throw this out for whatever it's worth, but, you know, from my perspective, I was a sniffer guy looking at sniffer traces, and I would read these different news things that would come out about John Postel and people like him who invented TCP, and almost with something like reverence when I would read about him. And I never really thought the IETF was a place for me. I thought it was, you know, maybe people at a higher level. But I learned from Nalini that it's a completely open organization. Anybody can go. And actually, I and people like me have a perspective. All the things I've tried to show you today is a perspective that the IETF crowd largely doesn't have and doesn't know. In the TLS working group, it's a lot of code developers, cryptographers and code developers, which they're smart, it's great work that they're doing, but it's a totally different world than trying to troubleshoot an internet banking problem. And we have a perspective that they need at the IETF. So we're trying to encourage people, like what happened to me accidentally when I ran into Nalini, that we really do need to get involved and find out what they're doing and try to influence the process. Because if you don't influence the process, you have to live with what they decide. And I think the outcome for TLS isn't pretty for people like me. So anyways, a couple other things happening just really briefly, but the Google folks have come out with a quick protocol, which is a kind of replacement for TCP that runs over UDP, and it's heavily encrypted from layer, not just application layer, but layer 4 encryption. And I'm very nervous about what Quick is going to do to my world. I'm not super familiar with it. I just think it's a problem. HTTP2 is all encrypted, as well as being binary. HTTP2 is tied to TLS 1.3, so I have some hope that a TLS 1.3 solution will also be an HTTP2 solution, but I'm not sure. Deprive is encrypted DNS, which is another problem. We need DNS for troubleshooting. I mean, we need DNS payload, and our security guys also need DNS payloads. They'll say, hey, you know, DNS request is going to a known malicious site, but as you hop through DNS servers, the source IP changes, so they don't know who actually sent this thing. And we need to be able to look back through the enterprise at DNS payloads to figure out who the infected station was. TCP increased security, again, is layer 4 encryption of TCP. I don't know all the details about it, but it makes me nervous. And then IPsec has been a long-standing issue for sniffer guys. You can't decrypt it unless you're using pre-shared keys, which not many people do. And IPsec is creeping into the enterprise data center for different reasons, like PCI, and it gives us blind spots if we can't decrypt it. So there are things going on besides just TLS that might motivate an enterprise person to find out what or a tool vendor, which I know a lot of those folks are here, might want to motivate us to find out what's happening at the IETF and try to influence the process and not just kind of passively, wait for the truck to hit us, which is kind of what's coming with TLS 1.3 if we don't deal with it. And then a couple lessons. This is my last slide, and thank you for your patience and attentiveness. Involvement with the TLS working group would have been a lot easier 3 years ago. When the RSA discussion first came up, I went back and read the email list exchanges, and nobody brought up anything remotely like what I've brought up today. They just had no concept of what consequences they were causing by removing our out-of-band decryption capability. So the discussion would have been a lot better 3 years ago. Now we've let them do 3 years of work, and they've got code. They all have code written. They're all ready to go. And to come in later in the process like we did is really painful. You can read the TLS email list from last September or from this June, July, if you want to see how painful it is. It's not easy to jump in and say, hey, you need to undo everything you've done for the last 3 years to meet our enterprise need. A second comment, this is anecdotal, but you can research it if you want. You can go to the IETF website, ietf.org, and you can see exactly who attends every IETF meeting. And in terms of what I'll call brick and mortar enterprises, for lack of a better term, there's almost nobody there. And people like me that do troubleshooting with sniffers, there's almost nobody out of 1,200 people that have this experience and mindset that I do. So there's a huge need for enterprise involvement, and decisions get made like the RSA key exchange decision just because our perspective just isn't there. There's a lot of browser vendors. There's a lot of what I'll call internet tech companies, Google, Facebook, Amazon, but they're really different than a US bank type enterprise, or I think a lot of other enterprises. So the perspective of enterprises is really needed badly. And the last thing I'll say, which Nalini may have alluded to, what we're trying to do is a complete culture change, right? They wrote a whole RFC that said Snowden-like monitoring is an attack and we are against it. We don't want anybody to decrypt packets ever and inspect anything, right? It's all kind of a reaction to the Snowden revelations, which there's some validity to that, right? There is government overreach in some cases in some countries, but there are also people like me in the private data center trying to keep the lights on. And we're using the exact same protocols used out on the wild internet, and we need capability to see stuff. So Nalini and I have been working on this problem, and Darrin started in Korea in November. We've been working on this problem for over a year, and we've made progress. We've gotten as far as a 50-50 vote. We've gotten up to our second draft, but we're a long ways from an actual implemented solution. So it takes years. It takes time. With that, I'll either turn it over to Nalini, or do we need a break, or do we want to keep going?
Let's do it. Let's do a quick thing. I have a couple things, and I know Darrin has a couple of things to say.
Okay. And
then we'll take a couple of questions, and then let's take a break. Yeah, no, thank you so much, Stephen. I'm going to speak a little bit from the IETF point of view. What I'd like to see, and again, every time I say this, I have to say this is Nalini's opinion. This is not the IETF consensus position. This is Nalini's opinion on what she would like to see at the IETF. And I'd love to see is like we have groups like the Internet, the Research Task Force. We have people like from Princeton, whatever, Cambridge, doing autonomic network monitoring. I'd like to see people like Steve having conversations, because a lot of what happens at the IETF is conversations. You know, you talk to people, and then all of a sudden you go, oh, I didn't realize, and then you end up developing a protocol, but it looks quite a bit different. As I say, I've been a part of it, and I've seen it happen. happen. And that's what I'd like to see. I'd like to see more Steves, because he can only talk to so many people. He's got a day job. Of course, a lot of people have day jobs, you know, and so this is what we need, is this whole perspective of the real feedback. In fact, I call it a feedback loop. Any organism that doesn't have feedback will die. And the ITEF cannot die. It's really just too important. And so that's the other way. We've got to get that loop in. And I know Darrin has, I mean, it's kind of interesting. We've all gotten so involved in this. You know, it's kind of it's a really important thing. I know Darrin wants to talk about some of what we've done here.